Okay, I'm now recording. Thank you very, very much for that reminder. All right, so 1D motion is movement forward and backwards on a single line. We sometimes talk about we'll call this rectilinear motion in some instances. I like to use 1D motion because it's a little bit more clear that 1D motion is related to 2D motion. Okay, so in rectilinear motion, we often use S to define position. And we say position is relative to some origin on this line. Okay, so we might actually have S extend back into negative numbers as well. But we'll set some origin S equals to 0. And the idea is that we want to track the motion of some particle that lies on this line as it moves backward and forward. And we'll say that because the position changes over time, position is then a function of time. All right, then we can define velocity and acceleration. Velocity is then v of t equal to the time derivative of position. So we will continue to use this annotation in this class where a dot over top of a quantity specifically indicates the time derivative, not any other derivative. Okay, so if I wanted to say ds dx, I cannot write that as s dot. S dot always means ds dt. Okay, so velocity is ds dt, and this dot notates time derivative. All right. Okay, I'm hoping this is a little bit of a review. So does anyone already know how this is related to acceleration? How does acceleration relate to velocity? It's the first derivative of velocity, right? So acceleration of t equals v dot, which is equal to dv dt. Now, if we wanted to say this in terms of position, I could say this is the second derivative of position. So dv dt is equal to d squared s dt squared. All right. Assuming some strong calculus skills and some remembering of these topics from calculus, I believe this is actually enough theory to go ahead and jump into our first example. Okay, so our first example for today, we're going to have a particle with some velocity traveling along a straight line. And we'll say that we know for some reason, we know that the velocity is equal to 6t minus 3t squared meters per second. And if we assume that the position is equal to 0 when time equals 0, we want to find three different quantities. I want to know what is the acceleration when t is 3 seconds, what is the position when t equals 3 seconds, and what is the total difference traveled by 3 seconds. Okay, so I'm going to split this up into the three different parts. I'll start with part A. We want to find acceleration, and we're given velocity. What do we need to do to that velocity expression to get acceleration? Take a derivative. Very good. So I know that acceleration is equal to dv dt. So that means I can take d dt of 6t minus 3t squared, which is equal to what? 6 minus 6t. Good, we remember some calculus. Now what? I want to know specifically at 3 seconds. What do I do? Plug in 3, yeah. Oh, snatches. Okay, plug in 3. At t equals 3, we get acceleration equals 6 minus 6 times 3, which is 6 minus 18 equals what? Minus 12, good. So acceleration for t equals 3 is minus 12 meters per second squared. How did I know it was meters per second squared? It's the units for acceleration if your velocity is in meters per second. Now, what if the velocity were in feet per second? What would acceleration be? Feet per second squared. That's correct. Yep. Heads up. You're in the middle. I'm going to take out like 8 people here. Oh, my bad. Okay, I tried. All right, that does it for part A. Woo, easy peasy. Part B. Let's do position. Position is weird because I have to go the other way, right? I don't take a derivative this time. I take a what? An integral. Very good. So I'm going to write down the relationship that I know. I know that velocity is equal to ds dt. And I'm going to do separation of variables. So I'm going to move this dt over to the left-hand side. I'll have v dt equals ds. And now all I need to do is throw in my integrals and my bounds of integration. And I'm going to go from t equals 0 to the t that I am concerned about, which is what? 3 seconds, yep. And so my bounds on my ds have to correlate with those time bounds. So I'm essentially saying I need to go from the position when time equals 0, which is what? 0. The position when time equals 0 is 0. And then I go to what? I'm setting bounds on S. This was bounded by time. I go from initial time to a final time. This one's going to from initial position to a final position, which is what it's asking me for, right, in the problem? So I'm going to leave that as a variable. I'll say S final. Trick question. Okay. Now I need to just toss in my expression for velocity and then evaluate the integral. So I'm going to take the integral from 0 to 3 of 6t minus 3t squared dt equals the integral from 0 to sf ds. What's my integral for this expression here? I'm hearing lots of muttering. It's all probably correct, so I'll go ahead and do it. 6t squared over 2, right? So I raise the exponent by 1, divide by that new exponent, minus 3t cubed over 3, and then I need to evaluate from 0 to 3. On the right-hand side, what is the integral of 1 ds? Just s, yep. And I will evaluate that from 0 to SF. Okay, so now let's plug in our limits of integration. I plug in the top number minus plugging in the bottom number. Okay, so I'll have 6, 3 squared over 2 minus 3 cubed over 3 minus, when I plug in 0, the first term's going to go to 0 and the second term's going to go to 0. So that's all just 0. On the right-hand side, I'll plug in SF minus 0. All right. You can use your calculator. You can do mental math however you'd like. We should end up with SF equals to what? 0. That seems odd. Why does that seem odd? I started at 0, and then I'm at 0 again 3 seconds later? What must have happened? It must have changed directions. Thank you, Samuel. Yes, so I started at 0. I went somewhere else. It's not really clear at this moment whether we went to the right or went to the left. But we started at 0, we went somewhere else, and then we came back. So if I started out to the right, I at some point had to turn around and come back. Okay? All right, so SF equals 0 meters, or you can say S when t equals 3 equals 0 meters. Okay, that realization that you have gone away from the origin and then come back is going to be really important for finding the total distance traveled, right? So if I started out at one spot and I only went in one direction for 3 seconds and I stopped, the total distance traveled is just wherever I am at that point. But because I turned around, if I choose this position as the total distance traveled, I'm missing all that part where I overlapped myself. Okay? So let's do total distance traveled. Let me give a little bit of logic here. We know that the particle starts and ends at s equals 0 meters. The velocity expression tells us that the particle must change direction at some point. Thinking back to our calculus days, what happens to velocity or position or acceleration when you're changing direction?
Zero.
What's zero?
The velocity.
Absolutely. The velocity has to be 0. So if you start out with a positive velocity, meaning you're going to the right, I think this is actually left for you. Regardless, you start out with one velocity, you have to go the opposite direction. You have to go in the negative direction to go in the opposite direction. You have to have negative velocity to go in the opposite direction, which means that you have to have crossed 0. At some point from having a positive velocity to a negative velocity, you have to have crossed 0. Okay, so how many times do we think this parabolic velocity, parabolic because this t is raised to the second power, how many times does it go to 0? Okay, probably twice. What we're going to find is one of those times is at a negative t value, which is weird, right? Negative time, what is that? And the other one is at a positive t value, which we're super happy about, okay? It turns out we'll only really care about the positive t value, okay? So we need to find out, first off, we need to find out whether the particle initially travels to the right or to the left, and then we need to figure out where it stops, okay? Okay, so to set our intention, we want to try to find out if particle initially travels to the right or left. What can we do to try to figure that out?
Try to t.
Oh, go ahead.
Try that t equals 1.
Yeah, very good. I would actually probably try an easier number to start out with. My initial thought would be plug in t equals 0 and see what direction it's going. However, that actually doesn't help us here because at t equals 0, what's my velocity? 0. 0 isn't going left or to the right. Yeah, so let's plug in t equals 1. At t equals 1, I have 6 minus 3. Is that positive or negative?
Positive.
Positive. So now we know that we are initially moving to the right. V of t equals 1 equals 6 times 1 minus 3 times 1 squared equals 3, which is positive. Then we need to figure out when does the particle change direction. And you already told me this happens when v goes to 0. So let's set v equal to 0. We have 6t minus 3t squared. I can factor the right-hand side. I'll get t outside of 6 minus 3t. And this expression goes to 0 when t equals 0 and when 6 minus 3t equals 0. So t equal to 2. Yes?
Could we use the fact that the acceleration
I don't think so necessarily, because you can decelerate both to the left or to the right. It just means that your velocity quantity is decreasing. I'd have to look exactly at how the negatives work on that, because I think if you're decelerating in the negative direction, it should be a positive acceleration. I don't know. That one hurts my brain.
Okay.
I'd rather think about velocity. I'd have to think really carefully about it. Okay, so what do we know? What does this tell us? This tells us what? Why do I care? Yep.
That's when it's changing direction.
Yes. Tell me in terms of position. It means that I have reached my what position? My maximum position. Yep. Yep, I owe some candy out. Absolutely. So now what do you think I need to do? Take that 2 seconds and find what?
Position.
Find out what position I'm at. Yeah, find that max position. Woo. All right. So we must reach its furthest location when t equals 2 seconds. So if we wanted to draw out the behavior of this particle on the s-plane, at t equals 0 and at t equals 3, we're at s equals to 0. We know that this particle goes out to the right, and somewhere in there it turns around and comes back. And this happens at t equals 2 seconds. But now I need to find out that position so I can find my total distance traveled. Okay, so our next question becomes, what is the position when t equals 2 seconds? If I go back to my position expression up here from part B, I can actually save some work. I can grab this line here and just change my bound of integration. Instead of going to t equals, oh wait, that's velocity. Is that velocity? No, that's right. Yeah, that's right. Copy. I can just change my bound of integration from going to t equals 3 to going to t equals 2. T equals 2. Great. Same integral. 6t squared over 2 minus 3t cubed over 3 from 0 to 2 equals SF. Skipped a couple of steps there. Yes?
Why did you bother finding whether it went to the right or the left if you're just going absolute value of total distance?
Mostly because I wanted to be able to draw this visual of what the particle was doing and correctly tell you whether it's going to the right or the left. But honestly, it's a very good check. So if it had started out going to the left and you got a positive position as its maximum position, that's a disconnect that would tell you something went wrong somewhere, right? You can't have started at 0, gone to the left, and gotten to s equals what we're about to find. Okay? All right, so let's do this. We've got 2 squared minus 2 cubed minus 0 equals SF. This should be 4 times 3 is 12 minus 2 cubed is 8 equals 4 meters. So we got a positive 4 meters. So this up here is 4 meters. Which means my total distance traveled is what? 8 meters, right? Beautiful. I go out, I come back. Sweet, we did 1 dimension, hooray. Let's do 2. Let's add a direction of motion. Everything is going to be basically the same. All the relationships are the same. The only difference is that we're going to move from scalar quantities. Notice that in nothing that I wrote up here did I put a vector bar. Nothing has a vector bar. I did that very, very carefully because these are all scalar quantities. However, in 2D motion, we have all the same relationships, but we're going to keep up with both an x component and a y component. And that total quantity is going to be a vector. Okay, so let's say I have an xy plane, and I have some particle in green here, out in this xy plane, and I want to track the motion of that particle through the xy plane. The first way that I can do that is by tracking its position. We do so with this r vector. We call the r vector the position of the particle, and it depends on time, or it can depend on time. And I'm going to write it like this, but I'll give a little explanation. This is an extremely general way of writing how you might break up a vector into two different components. So all I'm saying here is I'm going to call everything that multiplies by the I component, I'm going to say this is the Rx component of R. So all I'm saying is that we have this vector R, and some amount of it, I don't know how much, but some amount of it goes in the I hat direction, and some amount of it, Ry, goes in the J hat direction. Just a really quick review of I hat and J hat. Those are really, really special vectors. And they're so special that we don't give them the usual arrow hat. We give them this little hat. Why? Yep. They are unit vectors. Ooh, gold star for the day. Yes, what is a unit vector? Do you know?
Yeah, it's only, it's, the position of the vector is like one unit, I guess, just like one measurement.
Beautiful, yes. A unit vector is a vector with magnitude 1. But I and J are very special unit vectors. We say that I is the unit vector that points in the x direction, and J is the unit vector that points in the y direction, okay? And I've drawn them here, all right? No matter what unit or what coordinate system you choose, the way that you break up a vector into components is by saying that some amount goes in the same direction as some unit vector, and some amount goes in the direction of this other unit vector. So that's exactly the way that it's written. Okie dokie. So we've got position. So position, that vector is literally the vector from the origin to the particle. And now we need to talk about velocity. So velocity we write extremely similarly. Velocity is a function of time, and we say there is some x component of velocity that might depend on time, plus some y component of velocity that might depend on time. Sorry, that's getting really squeezed over there. How else can I write this? Can I write this in any relation to position? Say? Okay, we can say that v of t is equal to r, the vector itself, dot. It is the time derivative of the r vector. Absolutely true. I can even decompose each component that way, and I can say that, in fact, vx is equal to drx dt, right? The time derivative of this component, plus dry dt. These are all different ways of writing the exact same thing. Who knows how this vector velocity is related to this word speed? And no, it's not a drug. Yeah?
The absolute value.
So close. Not absolute value, but you want to change it slightly?
Scalar.
Let's. Not quite there either.
What is a vector?
No.
The magnitude.
It is the magnitude. Yes. Okay, so absolute value. Absolute values and magnitudes are actually kind of related in terms of like distance metrics if you go into the deep math of all of this. But magnitude is a different quantity than absolute value. So let's talk about what a magnitude is. The magnitude of a vector, if I have a vector A and I say it has some amount in the x direction, some amount in the y direction, the magnitude of A is the square root of each component squared. Which means that speed which is the magnitude of velocity, is equal to what?
Square root of dxt squared plus byt squared.
You got it. What's your name?
Scar.
Scar. You got it, Scar. Vx squared plus Vy squared. Excellent. Cool. Left-handed. Okay. I think that's about all I want to say about velocity, except one last thing. If we were to draw the path, the way that this particle moves through space over time, if every time it maybe laid down a trail of ink as it flows through the xy plane, the velocity vector is always, always, always going to be tangent to the path. So tangent to the path looks something like this. Okay, if the particle were over here, it'd be something like this. Velocity is tangent to the path. It does not matter whether you use Cartesian coordinates, x and y, like we're doing today, or if you use a different set of coordinates, like we're going to do in later classes. The velocity vector itself is always tangent to the path. That is always geometrically true. All right, let's move on. Acceleration. Sorry, I'll go ahead and make that explicit. Velocity vector is always, get out of here, vector symbol, always tangent to path. Okay, acceleration, also a function of time. Ax t in the I hat, that's terrible I. Plus a y t in the j hat. Another way to write this, time derivative of the x velocity, I hat, plus time derivative of the y velocity, j hat. Another way to write this, second derivative of the x position, dt squared, I hat, plus second derivative y position, dt squared, j hat. All different ways of writing the same thing. Yes?
Are we gonna have to parameterize any of our own like position curves?
What do you mean?
Like in Calc 3 where we have to do that? Are you guys gonna make us do that too?
So do you mean that if you're given a trajectory in terms of x and y, that you need to find x in terms of t and y in terms of t?
Yeah.
Yes. Yep. Okay, let's ask a couple. Oh, God, I'm sorry. Let's ask a couple of concept questions that might or might not be important for later assessments. What is this possible or not? I'm going to go through a series of cases. Which of these is possible? Is it possible to have constant acceleration but zero velocity? Robert? Yeah, absolutely. So let's say we're looking at maybe, what you tell me, Robert, what would be the case where that would happen?
Velocity is 0 and acceleration.
Okay, so you go to the 0, 0 case. It actually doesn't have to be 0, 0. What's another case where where maybe acceleration is non-zero? Yes, yes, yes. Velocity changes direction. So if I have t and v and my velocity starts out negative but becomes positive, the slope of this thing is the acceleration. That was a terrible slope. The slope of this line is the acceleration of my particle. It's a time derivative, right? But at some point, my velocity became 0. Okay? The slope stayed the same the whole time. The acceleration stayed the same, but velocity started out negative, it became 0, and then it became positive. Okay, so yes, this is possible. All right, the next one. Can we have constant velocity and 0 acceleration? Yep.
Yes.
Absolutely. It's kind of the definition of having constant velocity, right? If acceleration is anything other than 0, your velocity will not be constant. Okay, so constant velocity, 0 acceleration. Yes. Can we have negative acceleration but positive velocity? I heard a yes. Do we say yes?
Yeah.
Yeah, how is that?
Something was going really fast and is now slowing down, but still going fairly fast.
Beautiful. I'm going to the right really, really, really fast, and I slow down. I'm still moving to the right. I still have positive velocity, but my acceleration decreased. My velocity decreased, but is still going in the positive direction. Okay, so yes, that is true. Last one, can we have positive acceleration and negative velocity?
Yes.
Yes, why?
Same as last one, but the other direction.
Same as last one, but the other direction, right? Negative velocity means I'm going to the left. Positive acceleration says I'm going to the left less aggressively over time. But I'm still continuing to go to the left. So yes, every single one of these is possible. All right, let's move into an example for 2D. Give you a little bit to write this down. So we have a very fancy-dancy radar. This radar is looking for suspicious aerial vehicles in the area. That's really hard to say. Say that 5 times fast. Radar tracks the motion of a suspicious aerial vehicle P relative to the origin shown here. In the first 8 seconds after locking on to P, the recorded motion is as follows. And I have an expression for the position as a function of time. Your job is to find the velocity of P, the speed of P, and the acceleration of P. Okay, so like I said, the mechanics of this are going to be exactly the same as for 1D, but now I just need to keep track of 2 components at the same time. Okay, so let's go ahead and do part A, or velocity, together. What do I know? What is the expression that I know for velocity? How is it related to what I've been given? It's time derivative of the position, yeah. So velocity vector equals the time derivative of the position vector. Heads up. Yep. All right, so let's go ahead and take the time derivative of my position vector. V of t equals d dt of 225 plus 2.13 t cubed. This all belongs with I hat, plus 225 plus 0.993 t cubed. This all belongs with j hat. If I go ahead and evaluate those derivatives, I just have 6.39 t squared I hat plus 2.97 t squared j hat. And I should have given you that this position is given in meters, so velocity is in meters per second. Okay, last time we plugged in a t value. Why am I not doing that here?
I asked you for the general representation of the velocity, not a particular one.
It didn't ask for a particular time. Okay, it didn't say what is the velocity at t equals 3 seconds. It just said what is velocity. Okay, so it's safe to assume there, if you're not given a particular time value, that it's wanting the function of time. So we can leave it just as it is here. We don't need to worry about plugging in a t value. So this is my final answer. Notice that when I get to a final answer, what am I doing in our notes here?
Circling that.
I'm circling it or boxing it. I'm not going to take off points if you don't, but I highly, highly, highly recommend that anything you submit for this class, you box your final answer because it makes life easier for the grader. And trust me, you want the grader happy when you are like the 88th person whose work you are grading. So make it easier for your grader. Please box your final answers. All right, last one. Or not last one, we have 2 more parts. Speed, what do I do here? I gotta find the magnitude. Very good, what's your name? Tyreek. Glad to have you, Tyreek. Speed is equal to the magnitude of velocity, which is the square root of each component squared. Okay, so each component, I need to grab the I component first. 6.39 t squared plus 2.97 t squared. What are the units for speed? Meters per second. It's the exact same as velocity. Meters per second. Okay, and again, because they didn't give me a t value, this is my final answer. That's all I'm going to do to it. I am not going to try to reduce that or anything. Last part, C. C is asking for the acceleration. What is my known relationship between acceleration and some expression I already have? Time derivative of velocity, right? I've already found velocity, so that's a good relationship to draw on. If I hadn't yet found velocity for whatever reason, maybe the problem didn't ask me for velocity first, I could also relate it back to the second derivative of position. 6 to 1, half dozen the other. All right, so acceleration, ooh, tell me you can write. There we go. Acceleration as a vector equals dv dt. So dv dt equals the time derivative of exactly what I boxed for part A. So we should get 12.78 t I hat plus 5.95 t j hat. And what are the units? Meters per second squared. Very good. Okay, time to take the training wheels off. The next one is all you. Example 3. So we're going to do our first example of think, pair, share here. We go to 145? Yeah? All right, let's give you somewhere between 5 and 10 minutes to work completely alone. Okay, so I want it pretty quiet in here. You're going to work all on your own. At some point, when it looks like people are getting lost or completed, I will have you guys pair up, talk for a couple more minutes, try to get further along in the problem, and then we'll come back up to the front and I'll put the solution on the board. Okay? All right, so about 5 minutes, ready, go. I apologize for my pitiful drawing of a car, but you'll have to take my word for it, that is a car.
It's better than my recreation for a car.
Fair enough.
Is there any way that you can just make it like slightly bigger, so
I think that still has everything you need.
well, that's perfect.
Okay, great, sweet. Please continue to ask that. If I can ever make something better for anyone, let me know.